Welcome back. In this lecture, we'll be addressing the issue of liquid vapor transition of a pure substance. So before we get started, we need to be clear of the terminologies. So we need to be able to differentiate what we mean by vapor, what we mean by gas, and two associated terminologies, evaporation and boiling. How do you differentiate all of them? So first, let's get started with boiling. Okay, so by contrast, we can differentiate the other process. So what is the process we are considering? So I have a column of liquid, let's say in a beaker. It's an open container. I'm heating the beaker. All right. So how do you define boiling? Boiling occurs when the vapor pressure becomes equal to the superincumbent pressure. What exactly do we mean by that? So you have the column of liquid. As you boil, the contribution of vapor pressure to the total pressure increases, right? So let's say you keep boiling water. So the water vapor contributes to the total pressure. And as you increase the temperature, that contribution keeps increasing. And what is superincumbent pressure? That is the pressure that exists above this liquid column. So in this case, if it's an open container in atmosphere, it's 1 atmospheric pressure. So as you keep increasing the temperature, the vapor pressure at some point becomes equal to 1 atmosphere. Okay, so the entire pressure above the liquid column is made up by the vapor pressure of water. So that's when the liquid boils. There's a phase change of the liquid to steam, right? So that's what you mean by boiling point. So typically when we say gas, we're referring to something in the gas phase which is above its boiling point. Okay, so when we talk about vapor, we are referring to this thing that's in the gas phase, but it's below the boiling point, right? So going by these definitions, evaporation can occur below the boiling point too. Okay, there's a typo here. Evaporation continuously increases with temperature, and evaporation almost as an exponential increase with temperature as it gets close to the boiling point. So this is an important process. It is there in many, it shows up in many contexts, like refrigeration, in this part of North India, in summer when there is no moisture, in this time when there is no moisture, there's not much of rains, we use a kind of an air cooler which operates by evaporative cooling. Okay, so there is a phase change involved. That is why the air gets cool, but we will talk about this at a later stage. And then there's a reactor control. Supposing the reactor temperature keeps increasing, let's say because of an exothermic reaction. The one way to put down the temperature is, let's say you dump a liquid, let's say the water itself. Water might have the effect of diluting, but it also has an important effect of removing heat from the system. Why does dumping liquid water into the system remove heat? Because water is a dipolar liquid. That is, it's made up of dipole. So it has significant latent heat of vaporization. So the heat in the system is used for evaporating water to water vapor, right? So that's a very easy way of controlling temperature. So you could dump liquid water and the heat is removed by evaporating liquid water to water vapor. So these liquid vapor transitions have a lot of applications. We will look into these applications later as we progress in the course. Just we are trying to set up the fundamentals here. So whenever we are thinking about an abstract concept of, let's say, liquid vapor transition, we should have some idea on how we are going to realize what we are talking about. Physically, what kind of experiment we'd be doing, right? So it has certain idealization. For example, I will tell you what kind of experiment we can do and in what way it is idealized. So you have a column of liquid. It's at 1 atmospheric pressure. So it's a closed container. The container is closed by a massless lid. Okay, so the only role of the lid is to close the system. Okay, there's no mass exchange of this liquid in any direction, and this lid only solves that purpose. And then there is 1 atmosphere above this lid also. And then when you heat the system, it allows heat to come in, and you will have this intuition that when you supply heat to the system, this liquid will tend to expand. So there is intermolecular spacing between this liquid. Even though liquid itself is a condensed medium, there is some amount of intermolecular spacing, and that intermolecular spacing increases, right? So what is happening? The liquid molecules is jostling around. As you increase the temperature by supplying heat, as I've said previously, temperature is a measure of average thermal energy in various degrees of freedom. Here, the degrees of freedom is, let's say, vibration degrees of freedom. As it keeps jostling, it bumps into each other more and more rapidly. So there's a slight expansion. To accommodate this slight expansion, this liquid, this lid, which is covering, moves in a way that there's no friction between this lid and this piston, so to say. Okay, so these are two idealizations. There's a massless piston. See, this kind of thing you'd have heard from your high school, right? You always you've heard about this in the pulley problems which you did in high school. Probably you heard about a massless string and frictionless pulley. Okay, so these kinds of abstractions, idealizations are always possible, and that helps you in analysis. Okay, so we are thinking about a massless lid which moves without any friction. So as you keep supplying heat, the temperature increases, the volume expands. So at this, let's say we are thinking about water. So at 100 degrees centigrade, the water is ready to boil, right? So first here, there is no vapor. Okay, so the entire volume is only made up of water. As this column of water, the temperature is increased from 20 degrees centigrade to 100 degrees centigrade. There's no vapor as formed at 100 degrees centigrade. This column of water is ready to form gas. So what is you've learned from your high school, that this column of water, when it hits 100 degrees centigrade, even though you are supplying heat, the temperature does not increase, right? That's where the latent heat comes in. So this heat supplied, you call it as sensible heat, right? That is, there is heat that is supplied goes towards increasing the temperature. Okay, it makes sense. So you don't call this nonsensical heat, but you call it latent heat. This, as it hits 100 degrees centigrade, even though you're supplying heat, there's no temperature rise. So what does it do? The temperature, the heat that is being supplied goes into converting liquid water into gaseous water. Okay, there's a phase change in water. There is a significant change in volume, right? So when you go from here to here, the volume change is marginal. There's not much change in volume. But when you go from here to this particular state, there's a significant change in volume, because the density of gas, okay, so is much less than the density of the corresponding liquid. So there's a significant change in volume. Okay, so this is not a leaky container, so there's no gas escaping. So this lid moves without any friction. So when you continue to supply heat, this would continue to expand, all right? So with the temperature increase again, okay, so that's again sensible heat. Only from here to here, where the temperature remains a constant, you call it latent heat. But here again, there is sensible heat. So it would just amount to expanding this gas that has been formed. All right, so this is a physical process we are thinking about. This can be accomplished by experiments. So how do you represent this in terms of a phase diagram? So what are we plotting here? So we are plotting temperature. That needs no explanation. Here we are specifying along the x-axis. We are specifying. We are plotting specific volume, right? Volume per unit mass. Right. So that's what we are plotting. That's indicated by this symbol, this temperature. So let us. This is called compressed liquid. This phase, right, from here to state 2. This is called compressed liquid. What do you mean by that? What we mean is when you expand, when you supply heat, this liquid continues to expand, but still there's no phase change. It is just the liquid. Okay, so this region of the phase diagram is called compressed liquid. At this point, you call this point called saturated liquid, a liquid that is just about to boil. Okay, so any small amount of heat that you supply, it will form gas. Okay, that point is called saturated liquid. So we will come to saturated mixture later. So this point 4 is called saturated vapor. Okay, so here any amount of when you're in state 4, when this system is in state 4, any heat that is removed, okay, will give rise to a liquid. Okay, again, will give rise to phase change. That point is called saturated vapor. All this, when you go from 4 to 5, you call that superheated vapor. Okay, these are some terminologies. Okay, many things have come due to certain historical reasons and so on, but you should just be aware of these terminologies. All right, so it is important to note the entire process we are considering occurs at 1 atmosphere. There's no change in pressure at all. All right, so it's important. This is an equilibrium system in the sense that at each point the system is in equilibrium. Okay, there's no motion. All right, so these are all what you call quasi-static changes. So even when this vapor expands, when there is a movement of this piston, lid of the piston, okay, so that occurs in very slowly, such that the equilibrium is maintained. There are no dissipative forces, there's no friction, this pressure in the entire system remains the same. Okay, when there's a pressure difference, there can be flow and so on, which can give rise to viscous dissipation and so on. Nothing like this exists. So this is again an idealization of a process, quasi-static processes. So the entire system we are is an equilibrium. That's the process we are talking about. Even when there's a transformation, we are talking about a quasi-static transformation. All right. So the thing which we didn't look at is in the previous slide is the saturated mixture. So let's take a point, state 3. What is a saturated mixture? So when we got from state 2 to state 4, we went through a process where as you go from state 2 to state 4, more and more liquid goes into the gas phase. Okay, so state 3 is this state, which has two-phase system. Okay, so there is a liquid phase as well as a vapor phase. These are a particular kind of a liquid. There's not a compressed liquid, but a saturated liquid. What do you mean by that? As I give some more heat to the system, there's a phase change from the liquid to the vapor. What do you mean by saturated vapor? As I remove heat, okay, in this case, I talked about supplying heat. In saturated vapor, when I remove heat, there's a phase change. there is a condensation of vapor to a liquid. Okay, so this entire two-phase system is comprised of saturated liquid and saturated vapor, right? So this is a 50-50 by volume, it's 50-50. There's half of saturated liquid and saturated vapor. That's the state 4. So as I go from 2 to 4, the extent of vapor keeps on increasing. There is no saturated vapor. Here, there's no saturated liquid. Here, there's no saturated liquid. Okay, so this is the two-phase system. However, here there is a single phase. Here also there is a single phase. Okay, so this is one of the simplest phase diagram you can visualize. So for a pure system here. All right. It's also important to understand that the entire transition can be reversed, right? So what do we mean by that? So when we supply heat, we are going from state 1 to state 2 to state 3, 4 to 5, right? With corresponding change in specific volume, temperature, and the pressure is not changing. But if you consider the reverse process of removal of heat, okay, so removal of heat seems to be a bit complicated, more complicated experiment. Right? This can be a Bunsen burner, right? So we know how to think about this, but the contraption for removing heat can be done by refrigeration and so on. But that looks slightly more complicated, but this can be accomplished and you see it often, right? In refrigeration, air conditioning, you're removing heat constantly, right? So when you remove heat, you can go from 5 to 4, 3 to 2 to 1, right? So the entire trajectory can be reversed with the corresponding and the same change in temperature and specific volume. Okay, so this is the ideal feature. These are the features of an ideal process called these quasi-static process. Quasi means what? Almost static. Any transformation occurs there's an infinitesimal change from one state to another. All right. So there are these terminologies are quirky. Okay, so there is sometimes they defy logic. I'll tell you why. So if you are calling this is compressed liquid, I would have thought that this would have been called as an expanded vapor, right, or expanded gas. Okay, it's not so. Okay, so you call this superheated vapor, right? For why, we don't know, right? So, but that's the terminology, superheated vapor. If you call this superheated vapor, you should be calling this super cool liquid, right? Super cool liquid is not a liquid that is cool, right? That's not what we're talking about. So actually super cool liquid is nothing to do with liquid vapor transition, okay? So there is a terminology called super cool liquid because when you freeze a liquid, when you convert liquid water to ice, there is a phase transition that involves nucleation and growth. If you suppress liquid, you can have liquid water even below 0 degrees centigrade. Even you can go to minus 20 degrees centigrade, but still you need not have ice. Okay, so we look at this at a later stage when you look at phase diagrams with greater detail. But that state of a liquid that exists, let's say even at minus 20 degrees centigrade, without the formation of ice, that's what is called supercool liquid. Okay, so this terminology, superheated vapor, cannot be converted here. So this region, okay, between 1 to 2 is actually called subcool liquid. Okay, not a supercool liquid. Okay, so these are all quirky terminologies. You just have to be careful about these terminologies. Okay, there's nothing really conceptual about it. Okay, so we mentioned that liquid boils when the vapor pressure becomes equal to superincumbent pressure, right? So what if the superincumbent pressure changes, right? So when you, let's say you increase your elevation, okay, so you're in summer, you go from, you're somewhere at mean sea level, you go to a hill station and you try to boil water. So as you increase the elevation, the pressure decreases, right? The extent of atmospheric column decreases. Therefore, the atmospheric pressure, what we mean by atmospheric pressure, that also decreases, right? So how does the boiling point change with pressure, right? So you would think that boiling point will decrease, right? So you can also consider the other issue of if you increase the superincumbent pressure, how does the boiling point change? Okay, the boiling point would tend to increase. In the previous case, when the superincumbent pressure, when you go, the boiling point might decrease. You can also have cases where the boiling point can increase. Right, so this is what we are trying to say. So when the pressure increases, the boiling point, or this is called saturation pressure, increases. The saturation temperature, okay, will also tend to increase. So when we say 100 degrees centigrade, so if you extrapolate, I mean, if you see, this is approximately, this is atmospheric pressure. So this is all in kilopascal. Okay, so let's say atmospheric pressure, I say 101 kilopascal. So this is 100 degrees centigrade. That's your normal boiling point, let's say at 1 atmospheric pressure. But as you keep increasing the pressure, your saturation temperature, the boiling point will increase. When you decrease the pressure, the boiling point might it does decrease. Okay, so these have been documented in your textbook. So if you look at this, you can change the boiling point significantly, right? So if we are here, 1 atmospheric pressure, it's 100 degrees centigrade. If you increase as you keep increasing the pressure, your boiling point it does change, and you can also decrease these are important. Okay, these are very important for certain application. There is an application called freeze drying. Okay, so you want to remove water vapor from, let's say, for some food. Okay, you don't want to cool the material to a very low temperature. One way to remove water from such material is to evaporate at lower pressure. Okay, this is called freeze drying and so on. These applications are mentioned in your book, so you can go through it. So you should be aware of this. Okay, so let's go to another topic. So we are going to correlate a property with structure. Okay, we had introduced these notions of structure in the previous lecture. So what is that we want to rationalize? So we want to rationalize here latent heat. So latent heat of vaporization. So when we said that we moved from state 2 in the few previous slides, state 2 to state 4, what is happening? This structure, more and more structure is getting transformed from liquid to vapor phase, right? So what is happening? So when you say that's what you mean by latent heat, these are all associated with in this particular process is called latent heat of vaporization. So when in this state, when you supplied heat, supplied sensible heat, the heat that was supplied went into thermal motions. Okay, things were vibrating more and more faster, right? So if you count the number of bonds, more or less the number of bonds has not changed. Okay, supposing you melted from the solid to liquid, that phase transition has occurred, but you're in state 1, that's already liquid. As you go to state 2, if there's a notion of chemical bonds, number of chemical bonds, approximately we say the number of chemical bond doesn't change. What is changing? Just the kinetic energy available in each degree of freedom, that changes, all right? But when you go from 2 to 4, what is happening is you are breaking bonds. The heat that is supplied, that is being supplied to the system goes into breaking the hydrogen bonds. In this case, if you have water, the hydrogen bonds in this dipolar medium, which is water, these are fairly significant. Okay, so these hydrogen bonds are broken. Okay, the intermolecular bonds, intramolecular means that OH bond. That's what I mean by intramolecular. Intermolecular is a bonding between H2O molecule and another H2O molecule. Okay. So as I go from 2 to 4, why is there a latent heat of vaporization? Because the thermal energy that's being, heat energy that's being supplied goes into breaks chemical bond. Okay. So in the gas phase, there is no intermolecular bond. Okay. There is the bonding is negligible because the bond distances, the distance between, not bond distance, the distance between molecules is very large compared to distances between water molecules here. There's no bonding that exists. Sometimes they collide, but they usually you consider them to be elastic collisions. We will talk about this at a later stage. But what I want to emphasize here, there's no chemical bonding, intermolecular chemical bonding here, but there is intermolecular chemical bonding here. And there is a slightly different kind of intermolecular chemical bonding in a solid. Okay, so this is what you mean by latent heat of vaporization. So when there is also another latent heat called, this is a very, again, quirky terminology, latent heat of fusion. I know music fusion, I know dance fusion, okay, fusion between Western dance and Eastern dance. But what is the fusion? Here, the fusion is probably, again, probably connected with the caloric theory, right? We talked about in one of the previous assignment. Okay, so that's why we talked about fuse, this so-called fluid caloric fuses with ice to form water. Okay, maybe it came from there. I don't know, right? But just the way to remember, if fusion means freezing. Okay, so so when you are, let's say you're at 0 degrees centigrade, when you supply heat, the heat that is supplied goes into breaking the bonds of ice, solid, to form water. Okay, so this has a slightly different bonding environment compared to ice. Okay, this is not ice, right? The ice has a different crystal structure, but this is not ice. But I'm just trying to say that the latent heat of freezing is because of phase transition between solid to a liquid. But latent heat of vaporization is because of phase transition from liquid to gas. Okay, so that's the terminology you should understand. Okay, so if you, another question. Okay, so let us ask this question. So where is, there is a, when I think about the extent of chemical bonding changes, where is more change when I go from solid to liquid, or from when I go from liquid to vapor gas. Okay, so you would intuitively think, but the chemical bonding changes when I go from here to here is much more than chemical bonding changes when I go from a solid to liquid. Okay, so this must be also reflected in the extent of latent heat of the difference in latent heat of freezing when compared to latent heat of vaporization. Let's see whether you have to build such intuition. Okay, so it's all not measurements and data. Okay, so you have to make sense of data. I make sense of data by thinking about molecular properties. Everybody has a different way of building intuition, but whatever said and done, you have to build some intuition into what is being measured and what's being modeled. So, so let's build some intuition. So what this is all taken from Wikipedia. You can look at these numbers, okay? This is all not matter of measurements and data. So you should make sense of numbers. All right, so here latent heat of fusion, here latent heat of vaporization. And also you should have some feel for numbers. What are we talking about? What do we mean by 1 joule? How much is 1 kilojoule? How much is 1 kilowatt? Okay, so look at the environment around you. Look at the power required for running an air conditioner. Okay, 100-watt bulb. You know all these things, right? So you should have a feel for these numbers. How much does, when you say kg, okay, how much does it, what is a real kg? When you lift an object, you should be able to have some feel for all these numbers, okay? So let's look at this particular thing. I said that the chemical bonding changes. Here, is in vaporization is much more than here, right? So that is reflected in numbers. It's almost, let's say, 8 times more, right? So this number is about 8 times here, okay? Because there is significant change in chemical bonding here. And that is there almost in every place, okay? So if you see, it's almost 10 times here, sometimes even more, sometimes less, okay? Another thing, what is that? Melting point, okay? This is melting point is a indicator of strength of chemical bonding, okay? So helium, its melting point is not even denoted here, specified here, because it's a noble gas, right? So liquefy, you don't get to a solid. You can liquefy, but solid helium is tough, right? And so water, as I said, is a dipolar liquid. It's made up of dipoles, right? OH bond is a strong dipole. Okay, so dipole-dipole interaction is significant. Therefore, it has this particular melting point, and you should compare it with other things, right? So the nitrogen, because it doesn't have strong interaction, intermolecular interaction. So it is melting point is much less. So you should be able to make sense of melting point. As you get to lead, okay, so it's a strong bonding. Okay, it's still metal bonds. It's a metal. Here you have strong covalent bonds, and so on. Okay, so and then you should also be able to make sense of boiling points, right? Silicon, okay, to convert silicon to you have to vapor. Okay, so you have to increase the temperature much more significantly. Same thing for lead. Okay, so much more significantly. So what I urge you to do is, when you get some data, you think about two things. First, you should know how these things are measured. Okay, that's very important. Okay, so you should have a sense for how things are measured. Then you should also have a sense for these numbers. So you should be able to almost guess what is that. Okay, that's something which I tried to do for myself. Okay, so when I build some intuition, I try to guess if there's a new compound, okay, which has been introduced into the table. Can I guess the value without looking at the measured value? Okay, that's some kind of intuition you should be able to build. If you have these two things in place, you know how things are measured and have some sense for these numbers. The third aspect, how things are modeled, how do you develop a theoretical model, mathematical model, will also come more naturally. Okay, so I urge you, even though in this class, okay, we don't address all three aspects in much greater detail. Okay, so if you take up a job, all jobs, technical jobs, involve troubleshooting. Okay, go to research or go to industry. All these things will involve troubleshooting. This kind of intuition helps. Okay, so you should try to practice. Okay, so let me stop here. Thank you.